If I look at the next one, again, this is a cube root function. That's what the 1/3 power means. I can think of this as just shifting around a little bit. So inside with the x, well, let me draw my original cube root function. It looks like this first. It's that sideways version of what we just drew earlier because they're inverses. And now when I look at this thing, I want to shift it, and I'm going to take the center of this thing and move it around a little bit. So the +2 moves it to the left 2. That would bring me back to here. And then the -2 moves me down 2, which brings me back to here. So now I graph the same function, but I graph it at this location. It's going to look like this. Okay? And again, it doesn't really affect my domain and range, but I do want to be able to draw a quick sketch of this thing using my transformations. Okay, so now I've got a quick sketch of this thing. I can now see that the domain is all real numbers. I can see that the range is also all real numbers, and that's it. Okay? If I look at the next one, an e to the x function is just an exponential function that looks kind of like this. Multiplying by 2 on the outside is really just going to kind of move this thing around a little bit. It's going to multiply all of my heights by 2. So in other words, right here, this first value that was 1 unit high is now going to be 2 units high. The next value that was 2 point something units high is now going to be 4 point something units high. Okay, so it kind of makes this thing just a little bit more extreme, but it doesn't really change it that much, and it really doesn't affect it in terms of my domain and range. Remember, with my exponential functions, I end up with a horizontal asymptote here that I'm closer and closer to. And so now when I look at my domain is all real numbers, which is pretty typical for our exponential function, but my range is y is greater than 0. And notice it's not greater than or equal to 0 because I have a horizontal asymptote here. And this horizontal asymptote is y equals 0. And I'm going to get closer and closer to that line without actually touching it in this case. Okay? Same thing with the next one. If I take the original function, it's just kind of a generic exponential function. And the -2 up there with the x is going to move this thing to the right too. So I'm going to take this point right here because it's just an easy point to grab. And I'm going to take that point and move it to the right too, which is going to put me here. And then I'm going to move the whole function up 1, which is going to put me here. So now what I'm going to do is I'm going to graph that same function, but I've essentially moved this point to this location. Okay? And by moving that, I'm going to draw the same graph in a different location. It's just going to look like this. And so what happens here as I shift this thing around in terms of my domain and range is now this thing is hugging a different line. It's hugging a line that's up here. So I have essentially a horizontal asymptote at y equals 1, which means my domain is still all real numbers. That one didn't change. But my range is now y is greater than 1. And again, it's not equal to 1 because I'm going to get closer and closer to that asymptote without actually touching it. Okay? If we take a look at this next one, I want to just draw a quick sketch of this thing, and I'm going to include all the x and y-intercepts. So I'm going to start with the x-intercepts. To find the x-intercepts of any function, I just plug a 0 in for y. So when I plug a 0 in for y here, I'm just going to solve this by factoring because it's already factored. I set each factor equal to 0. The x minus 4 equals 0, and the x minus 2 equals 0, and the x plus 3 equals 0, and I solve each. So I find out that I have these x-intercepts. Try that again. And now I want to find the y-intercepts, or y-intercept. There's only going to be one this time. For any function, again, to find the y-intercept, I plug a 0 in for x this time. So I'm going to have y equals 1/2 0 minus 4 times 0 minus 2 times 0 plus 3. And when I do that, I multiply all this out. That gives me a 12. And so now I'm just going to plot all of my intercepts. I've got 4, which is over here, the 2, the -3, and then the 12 is way up here somewhere. But really that tells me exactly what this thing is supposed to look like. Because each of these is odd, they're all to the first power, it means I'm going to pass through the x-axis on each rather than just touch. And really there's only one option. I could find the end behavior, but I'm going to find if I do the end behavior that this end has to be going towards -infinity because I have to go up here, hit that y-intercept. So it's going to look something kind of like this. Okay? It's got to cross at all of those x values. It's got to cross at that particular y value. This is the only function that could be drawn. Number 22, we're working backwards essentially from what we just did. It's telling me that I have zeros of -4, 1, and 2. Those are X-intercepts, which means this would have come from a factor of x plus 4. This guy would have come from a factor of x minus 1. And this one would have come from a factor of x minus 2. All right? The only thing that could be different here is I could have some a value here that I'm not aware of. So it's y equals some possible constant value times these factors. And that's where the y-intercept comes in. That's going to help me narrow this thing down. In other words, this is the ordered pair 0, 2. I should get a 2 out here when I plug zeros in for x. So when I do this, over here I've got 4 times -1 times -2, which is going to give me a positive 8. I have 8a, and now I'm just going to divide to solve for a. And when I do that, I find out that a equals a 1/4. And now I can write my equation, y equals 1/4. Then I write my factors down that I already established earlier. Just had to find that a value to make sure I had the proper y-intercept. And that's it. If I look at the next one, it says direct and inverse variation here. So this first one, it says when y equals 10, x equals 12, if y varies directly. And direct variation, remember, is this guy, y equals k times x. And it's telling me that when y equals 10, x equals 12. And so what I'm going to do is I'm essentially going to solve for k. I need that k value. So I find out that k equals a 5/6, which means I'm dealing with this equation, y equals 5/6 times x. And then it says, what's the value of y when x equals 18? So I just simply plug in an 18 here for x to see what y is going to equal. And when I do that, I can reduce a little bit. Each of those is divisible by 6, really. So that's a 3/1. So I find out that y equals 15. And that's it. In the next one, it tells me that y varies inversely with x. So inverse variation this time, y equals, that's going to be k divided by x. It's essentially the same thing, but instead of multiplying the k value by x, I divide the k value by x. And I'm going to do the same thing. I'm going to solve for k. It tells me that this equals 10 when x equals 12. And to solve this one, I'm simply going to treat this as 10/1, and I'm going to cross multiply. So I find out that k equals 120, which means I'm dealing with this equation, y equals 120 over x. And I want to know what's y going to equal when x equals 20. So I've got y equals 120 divided by x, which is 20 this time. So I find out that y equals 6. And that's it. Okay? Number 25, we want to simplify this thing. And all I have to do to simplify an expression like this, since I'm multiplying, is I'm just going to factor everything completely and cancel out any common factors. In this numerator, I can factor out a 3. That's going to leave me with a 2x plus 3. In the denominator, I can factor out, actually, let me think about this one off to the side. So if I think about that denominator, the first thing I'm going to do is factor out an x squared, which is going to leave me with an x squared minus 4. And now an x squared minus 4 is a difference of squares. I'm just going to factor into an x plus 2 and an x minus 2. So what I have here when it's all said and done is an x squared on the outside, and then the x plus 2 and the x minus 2. I'm going to do the same thing with the other side of this thing, with the other fraction that's here. So in the numerator, I build a bridge, two numbers that multiply to a -6 but add to a -1. That's going to be an x minus 3 and an x plus 2. I do the same thing in the denominator. However, I can't take the same shortcut that I did in the denominator. So if I think of that off to the side here momentarily, I build a bridge that gives me a -6. Two numbers that multiply together to give me a -6 but add to a +1 are a +3 and a -2. And for this one, I have to split up the middle term. So I'm going to split it into a +3x and a -2x, and then the -3. And I've got to do factoring by grouping here. I group the first two together and the second two together. Out of the first two, I can factor out an x. Out of the second two, I can factor out a -1. So then my two factors are the 2x plus 3 and the x minus 1. And there are some shortcuts that you can use and apply there, but that's the official way to do it. So I bring this back over here. And now I just start canceling out any common factors. I see the 2x plus 3's are common. I see the x plus 2's are common. And it looks like that's about it. So this leaves me with a 3 times x minus 3 over x squared times x minus 2 times x minus 1. And that's it. I'm just going to leave it in that factored form. Okay? If I take a look at the next one I'm going to do the same thing with one extra step. I'm going to change that division to multiplying by the reciprocal. So the first thing I do here is I change that division to multiplying by the reciprocal. Now it's just like the previous problem. I'm going to factor everything completely, cancel out any common factors, and go from there. In the numerator, I can factor out a 4. That leaves me a 2x plus 1. In this denominator, I'm going to go ahead and just go right to factoring this. If you need to, feel free to take this thing off to the side. There's nothing wrong with doing that. That's going to be a 2x plus 1. And let's see, an x plus 4. Over here, this is going to be an x plus 4 times an x plus 4, which you could write as x plus 4 squared. I'm just going to leave it separated for now. Down here, that's an x plus 4 and an x minus 4. And the reason I left that numerator separated is just because it's going to be a little bit easier to see when I start canceling these things out. Here, these guys cancel. A pair of x plus 4s, another pair of x plus 4s. And so now what I'm left with in my numerator is a 4. In my denominator is the x minus 4. And that's it. Okay? If I look at the next one, again, I want to solve this thing. So if I'm solving this particular equation, the first thing I want to do is kind of identify the common denominators. And I'm not actually going to get common denominators here. I'm just going to identify them so that I can get rid of the fractions. Anytime I have an equation that has fractions in it, we want to multiply through by the common denominator in order to get rid of these. So if you imagine for a moment when I look across these denominators, if every denominator had all the same factors, there would be 3 factors involved. One of them would be the x minus 4. Another would be the x plus 2. And the last one that hasn't been used is the x minus 3. These are the 3 factors that are incorporated in my denominators. That would be my common denominator. And rather than actually get the common denominator, I'm just going to multiply each side by that common denominator. Okay? And when I do that, the effect that this has by just leaving this as something over 1 and just multiplying each side, and again, because it's an equation, I can do that. Over here, I get a couple of things that cancel. So what I'm really left with is the x minus 3 times the x minus 2. And over here, these guys cancel, which means what I really have is the x plus 4 times the x plus 2. And now I just have to multiply that out. When I multiply it out over here, I get an x squared minus 5x plus 6. Over here, that is a terrible looking plus line. Let me try again. Over here, when I multiply this out, that's an x squared plus 6x plus 8. And now I can go ahead and finish solving this thing. If I subtract the x squared from each side, I end up with a negative 5x plus 6 equals 6x plus 8. I'm going to rearrange this a little bit. I'm going to add the 5x to each side. So I end up with 6 equals 11x plus 8. I'm going to subtract the 8. And so this really becomes a relatively easy equation to solve once I get rid of those fractions. I'm going to find out that x equals, looks like a negative 2/11. And that's it. Okay? The only thing I might do is go back and check to make sure that's not going to be one of my domain restrictions, which is not. You can kind of see the domain restrictions of x can't equal 4, negative 2, or positive 3 from the denominator that we would have had. Okay?